The universe appears suspiciously well arranged. Numbers, ratios, and fundamental constants align with a precision that feels almost intentional. This is the cosmic coincidence problem, the unsettling notion that our reality might be built on a foundation of perfect accidents. In this exploration, you will gain a new perspective on everything from the vast emptiness of space to the chemistry in your own body. We will confront why the moon perfectly covers the sun, why the cosmos is so eerily silent, and whether the very laws of physics are a happy fluke. Is this all just random luck, or is there a hidden order waiting to be decoded? What does it feel like to question the basic nature of reality? This perfection begins with numbers. Not just any numbers, but the fundamental constants that act as the universe's fixed settings. Think of them as the dials on a cosmic control panel. One dial sets the strength of gravity. Another determines how tightly atomic nuclei bind together. A third controls the speed of light itself. The unsettling truth is that every single one of these dials appears to be set to a very specific, very narrow value. And if any one of them were turned even a fraction of a notch in either direction, the universe as we know it would vanish. Take gravity, for example. If the force of gravity were just a little bit stronger, all the matter from the Big Bang would have collapsed back in on itself almost immediately, creating a universe of black holes with no stars and no time for anything to evolve. If it were slightly weaker, matter would have flown apart so rapidly that galaxies and stars could never have clumped together from the primordial gas. We would have a cold, dark, and empty expanse. The same razor's edge applies to the strong nuclear force, which glues protons and neutrons together inside an atom's core. If this force were a few percent weaker, simple hydrogen would be the only element that could exist. There would be no carbon, no oxygen, no building blocks for planets or people. If it were slightly stronger, all the hydrogen in the early universe would have fused into heavier elements too quickly, starving future stars of their fuel and preventing long-lived solar systems like our own from ever forming. The list goes on. The exact mass of an electron, the precise amount of dark energy causing the universe's expansion to accelerate, even the delicate balance between the four fundamental forces, all seem calibrated to an impossible degree. This is the fine-tuning problem. It feels as though someone or something set these values with life in mind. Of course, one proposed answer is the anthropic principle. It simply states that we observe a universe compatible with our existence because, well, we are here to observe it. In an infinite multiverse where every possible combination of constants exists across countless different universes, we naturally find ourselves in one of the rare, habitable ones. It is a logical answer, but for many, it feels deeply unsatisfying, like explaining why your house did not burn down by saying every other possible house did. It answers the how, but it completely avoids the deeper why. Why does this particular set of rules, this specific and beautiful mathematical harmony, exist at all? The fine-tuning of the universe is not just a scientific curiosity. It is the first and loudest echo of a pattern that feels far too meaningful to be mere chance. That fine-tuning leads us to one of the most baffling numbers in all of science. If the dials on the cosmic control panel are set with impossible precision, then one dial in particular seems to be not just set, but actively broken. This is the cosmological constant problem, and it represents a failure so spectacular that it humbles our entire understanding of physics. It begins with a simple, profound question. What is the energy of empty space, not outer space with its occasional atoms and radiation, but true, perfect, absolute nothingness. According to our best theories of the quantum world, the vacuum of space should be a seething, bubbling foam of virtual particles constantly flickering in and out of existence. All that frantic activity should give empty space itself a tremendous amount of inherent energy, a background hum of the universe known as vacuum energy. Physicists can calculate what that energy density should be based on the principles of quantum field theory, and when they do, they get a number, an enormous, universe-shattering number. The theoretical prediction suggests space should be brimming with so much vacuum energy that the fabric of reality should have ripped itself apart in the first instant after the Big Bang. The universe, according to math, should not exist. Yet, when astronomers actually measure the energy of empty space by observing how the expansion of the cosmos is accelerating, they get a value. A very, very small value, not zero, but incredibly tiny. To put the mismatch into perspective, the predicted value is about 1 followed by 120 zeros times larger than what we actually observe. That is not a small error. It is not even a huge error. It is an error so vast it defies human comprehension. If the difference between prediction and reality were a physical distance, it would be like calculating the width of the entire observable universe, and then discovering the real width is smaller than a single proton. It is widely considered the worst theoretical prediction in the history of physics. This is not just a coincidence, it is a screaming paradox. The fact that the cosmological constant is not the catastrophic number we predict, but is instead a minuscule, non-zero number, is the first incredible stroke of luck. But the coincidence deepens. This tiny leftover energy, this faint whisper in the void, is not zero, and its specific, minuscule value happens to be just right for the universe we see today. It is small enough that it did not destroy the cosmos in its infancy, allowing galaxies and stars to form over billions of years, but it is also large enough and became dominant at just the right moment in cosmic history to now be gently pushing galaxies apart, driving the accelerated expansion we observe. If it were truly zero, the universe's expansion would eventually slow to a crawl. If it were even slightly larger, that acceleration would have begun much earlier, tearing structures apart before life could ever arise. So, we are left with a double mystery. Why is the energy of nothingness so unbelievably, inexplicably small compared to our predictions? And why is that small residue not nothing, but exactly the faint pressure needed to shape the destiny of the entire cosmos? It feels less like a calculation error and more like a cosmic correction, as if the universe itself is balancing its books with a precision that mocks our understanding. This impossible balancing act extends to the very shape of reality itself. Look around you. The room you are in has a geometry. The floor is flat. The walls meet at right angles. Now, try to imagine the geometry of the entire universe. Is it curved like the surface of a sphere, bending back on itself? Is it saddle-shaped, flaring outward in every direction? Or is it perfectly flat, like an infinite sheet of paper? For decades, cosmologists debated this very question. The answer, revealed by painstaking observations of the cosmic microwave background, the afterglow of the Big Bang, is astonishing. The universe is flat, not approximately flat, but exquisitely, perfectly flat. This is not a trivial detail. It is a cosmic condition so precise it defies belief. To understand why, think of the Big Bang as a launch. All the matter and energy in existence was thrown outward. The fate of that expansion, and thus the shape of the universe, depended entirely on a single factor, the initial density. If the density of the universe at that first moment was too high, gravity would eventually win. The expansion would slow, stop, and reverse in a catastrophic Big Crunch, a closed universe curving in on itself like a sphere. If the density was too low, gravity would be too weak to ever rein things in. The universe would expand forever, thinning out into a cold, empty, and open saddle-shaped void. For the universe to be flat, the initial density had to be exactly the critical value, perfectly balanced between these two eternal fates. And here is the coincidence, a number so fine-tuned it is almost meaningless to write down. Measurements tell us that within 1 second of the Big Bang, the density of the universe matched that perfect, critical value to an accuracy of 1 part in 10 to the power of 60. To put that number in perspective, it is like balancing a pencil on its tip, not just for a second, but for over 13 billion years, with such precision that if it had leaned by the weight of a single atom more or less at the start, the entire universe would look completely different today. This is the flatness problem. Why was the universe born in such an unimaginably precise state of balance? The leading explanation is a theory called cosmic inflation. The idea is that a fraction of a second after the beginning, the universe underwent a period of hyper-accelerated expansion, stretching space itself faster than the speed of light. This violent stretching would have ironed out any curvature, smoothing the universe into the flat geometry we observe, much like how inflating a balloon makes a small patch of its surface appear flat. Inflation solves the problem mathematically, but it simply pushes the coincidence one step back, for inflation to start and stop in just the right way to produce our flat universe. The initial conditions that triggered it had to be, themselves, extraordinarily special. It is as if you found a perfectly balanced pencil and explained it by saying a gust of wind set it upright. You still have to explain why the wind blew with such impossible accuracy at that exact moment. The flatness of our cosmos feels less like a natural outcome and more like a starting assumption, a foundational piece of fine-tuning written into the first line of the universe's story. This perfect flatness creates another, even more visceral mystery when we look at the oldest light in the universe. It is a problem of temperature, and it makes no sense at all. Travel to the deepest, darkest void between galaxies and point a sensitive radio telescope. You will not find perfect darkness. Instead, you will detect a faint, omnipresent glow of microwave radiation coming from every direction in the sky. This is the cosmic microwave background, the cooled and stretched afterglow of the Big Bang itself. It is the universe's baby picture, taken when it was only 380,000 years old. And this picture has a very strange feature. No matter where you look, the temperature of this ancient light is almost exactly the same. To be precise, it is 2.725 degrees above absolute zero, everywhere. That might sound reasonable until you consider the distances involved. Look at one patch of this ancient sky, then turn and look at the exact opposite side. Those two regions of the infant universe are separated by a staggering 28 billion light-years in today's expanded space. Here is the impossible part. Given the age of the universe and the finite speed of light, there has not been enough time since the Big Bang for light, or heat, or any form of information to travel between those two opposite points. They have been causally disconnected since the beginning. They have never been in contact. Think of it like 2 cups of coffee placed in separate, soundproof rooms that have never had a door between them. Yet, when you measure them, you find they have cooled to the exact same temperature, down to a variation of less than 1 part in 100,000. How could this happen? How could regions of space that have never exchanged a single photon achieve such perfect thermal equilibrium? This is the horizon problem, and it screams that something is missing from our story. For the cosmic background to be this uniform, the entire observable universe must have been in close, intimate contact at some early point, able to mix and equalize its temperature like water in a well-stirred pot. But according to standard cosmology, it never was. The only way to solve this is to propose that the early universe underwent a period of unimaginably rapid growth, a burst of expansion so fast it far exceeded the speed of light. This is the theory of cosmic inflation. It suggests that a tiny, subatomic speck of the primordial universe, a region small enough to have been thoroughly mixed and smoothed to a uniform temperature, was suddenly stretched to a size larger than our entire observable cosmos in a fraction of a second. This hyper-fast stretching would have taken that tiny region's perfect uniformity and imprinted it across the vast sky we see today, explaining the eerie sameness. Inflation elegantly patches the hole in our model, but it does so by invoking a process of such extreme and fine-tuned violence that it feels like another cosmic coincidence in disguise. Why did inflation start? What stopped it? And why did it stretch the universe by just the right amount to give us this specific, smooth, and flat reality, rather than tearing everything apart completely? The uniformity of the cosmic microwave background is not just a data point. It is a ghostly imprint, a frozen memory of a moment when the rules of reality as we know them were suspended, leaving behind a cosmos that feels suspiciously, perfectly prepared. That eerie uniformity in the ancient sky tells us the early universe was a remarkably simple place, a hot, dense soup of fundamental particles. From that simplicity, the very first atoms were forged. This process, called Big Bang nucleosynthesis, is one of the great success stories of cosmology. The calculations are breathtakingly precise. Within the first few minutes after the Big Bang, as the universe cooled from an unimaginable inferno, protons and neutrons began to fuse. The models predict exactly how much of each light element should have been created before the expanding universe cooled too much for further fusion, and for the most part, the universe obliges. When astronomers measure the oldest, most pristine pockets of cosmic gas, they find the amounts of hydrogen and helium match the predictions almost perfectly. It is a stunning confirmation of our understanding of the universe's first moments, but there is a crack in this beautiful picture. One element does not obey the rules. Lithium, specifically the isotope lithium-7. According to the pristine math of the Big Bang, there should be about 3 times more lithium-7 floating around in the oldest stars than we actually observe. The universe seems to be missing its lithium. This is not a small oversight. It is a glaring discrepancy that has stubbornly resisted explanation for decades. Why would the cosmic recipe work flawlessly for hydrogen and helium, but fail so consistently for lithium? One possibility is that our understanding of the nuclear physics itself is incomplete. Perhaps there is a reaction pathway we have not considered, a way for lithium to be destroyed in those first few minutes that our models do not account for. Another idea points to the stars themselves. Could the oldest stars, those cosmic time capsules we use to measure primordial abundances, be processing lithium in their interiors and subtly altering the signal we see? Or does the answer lie even deeper in the conditions of the early universe? Could there have been exotic particles present, like certain types of dark matter, that interacted with the nuclear soup and altered the yields? Each proposed solution tends to fix the lithium problem, but then throws off the perfect agreement we see with hydrogen and helium. It is a maddening puzzle. The lithium problem stands as a quiet but persistent reminder that for all our confidence, there is a fundamental piece of the early universe we do not yet understand. It is a single wrong note in an otherwise harmonious symphony, telling us the score might be more complex than we thought. The lithium problem whispers that our cosmic recipe might have a missing ingredient. But there is another feature in that ancient afterglow, the cosmic microwave background, that does not whisper at all. It screams. Scientists have given this anomaly a name that sounds like it belongs in a thriller, the axis of evil. It is a pattern in the oldest light in the universe that seems to know where we are. When researchers meticulously mapped the tiny temperature fluctuations in the cosmic microwave background, they expected to see a random, isotropic distribution. The variations should look like a static snowstorm on an old television, with no preferred direction or alignment. That is what a universe born from a perfectly uniform, random state should produce. But the data tells a different story. The large-scale patterns, the biggest waves in this frozen sea of light, are not randomly oriented. They appear to align. Eerily, they align with two specific planes in our own little corner of the cosmos. One alignment is with the plane of our solar system, the ecliptic. The other is with the direction of the sun's motion through the galaxy. This is profoundly strange. The cosmic microwave background is a signal from a time long before the sun, the Earth, or the Milky Way galaxy even existed. It is a relic of the entire universe when it was 1,000 times smaller than it is today. There is no physical reason, within our standard model of cosmology, for the largest structures in the primordial universe to have any correlation whatsoever with the orientation of our solar system, which formed nearly 9 billion years later. It is as if you found a fossil from the Jurassic period that had your own fingerprint etched into it. The statistical probability of this alignment happening by pure chance is incredibly low, less than 1 in 1,000. This is why it is labeled an anomaly. To cosmologists, an anomaly is not yet a discovery. It is a persistent itch in the data that could mean one of three things. First, it could be a fluke. With the vast amount of data we collect, sometimes unlikely patterns do emerge purely by random chance. Second, it could be a systematic error, some subtle contamination in our measurements that we have not yet fully accounted for, perhaps an effect from our own galaxy or the instruments themselves. But the third possibility is the most unsettling. It could be a genuine clue, a crack in our standard model hinting at a physics we do not yet understand. Some theorists speculate it could be evidence of something beyond our observable universe influencing our local geometry. Others wonder if it points to a pre-Big Bang structure, a fossil imprint from a prior cosmic phase that set a preferred direction for reality itself. The name Axis of Evil captures the feeling perfectly. It is spooky. It feels like a cosmic coincidence of the worst kind, a violation of the principle that we do not occupy a special place in the universe. The alignment suggests, against all odds, that the universe's oldest structure might somehow be linked to our own modern-day celestial address. Whether it is a statistical ghost, an uncaught error, or a whisper from the edge of reality, it remains one of the most chilling unsolved puzzles written in the light of creation. That unsettling alignment in the ancient light is mirrored by something far closer, a current in the cosmic ocean that is pulling us along. For decades, astronomers knew our galaxy was not sitting still. The Milky Way is moving, and not just in a simple orbit around the local cluster. It is rushing through space at a staggering speed of over 600 kilometers per second. But the question was, why? What could possibly exert enough gravitational pull to move an entire galaxy? The answer led to the discovery of a colossal, hidden structure and a profound cosmic coincidence. Our motion is not driven by one force, but by a perfect push and pull. We are being dragged toward a gravitational monster known as the Great Attractor, while simultaneously being shoved away from an immense cosmic void called the dipole repeller. The Great Attractor is not a single object, but a dense knot in the cosmic web, a supercluster of galaxies located about 150 million light-years away in the direction of the constellations Centaurus and Norma. Its gravity is so immense it is pulling thousands of galaxies, including our own, toward it. For a long time, its core was hidden from our view, obscured by the dusty plain of our own Milky Way, making it a literal blind spot in our sky. But the push is just as important as the pull. On the opposite side of the sky, in the direction of the constellations Gemini and Cancer, lies an almost unimaginable emptiness, a region hundreds of millions of light-years across containing very few galaxies. This is the dipole repeller. Think of it not as an object that pushes, but as a lack of pull. In the grand tug of war of gravity, regions with lots of mass pull you toward them. Regions with very little mass, these vast cosmic voids, effectively create a push because everything else is pulling you away from them. So our motion is the result of this precise balance, a river of galaxies flowing from the barren expanse of the dipole repeller toward the dense concentration of the Great Attractor. And here lies the coincidence that borders on the eerie. These two titanic structures, one an overwhelming concentration of matter and the other a staggering absence of it, are positioned almost exactly opposite each other in the sky relative to our location. We are caught perfectly between a gravitational sinkhole and a cosmic desert. This arrangement is what creates the specific, powerful flow we are part of. The question this forces upon us is unsettling. Is this just a local quirk, a random fluctuation in the sprawling cosmic web that we happen to find ourselves in? Or does it suggest, once again, that our place in the universe might be oddly special? If the distribution of matter and voids were perfectly uniform, there would be no net flow at all. But it is not uniform, and the particular imbalance we find ourselves within seems remarkably pronounced. It feels like we are riding a wave that was set up by the architecture of the universe on the largest scales, a wave whose crest and trough align with our position in a way that feels too convenient to be entirely accidental. This grand flow is a reminder that we are not passive observers of the cosmos, but active participants caught in its gravitational currents, currents that seem to have been arranged with a peculiar symmetry around our tiny galactic home. Our place in this grand flow offers a unique vantage point, one that reveals a coincidence so perfect it feels staged. From the surface of our world, the two most important celestial bodies in our sky, the Sun and the Moon, appear to be exactly the same size. This is not a metaphor. It is a precise geometric accident of cosmic proportions. The Sun's diameter is about 400 times larger than the Moon's. But by an almost unbelievable stroke of luck, the Sun is also roughly 400 times farther away from us than the Moon. These two immense ratios cancel each other out perfectly. The result is that both disks, when viewed from Earth, span almost exactly half a degree of sky. This precise alignment is what makes a total solar eclipse possible. During that breathtaking moment, the Moon slides directly in front of the Sun, covering its brilliant face completely while revealing the delicate, wispy tendrils of the solar corona. It is a spectacle of shadow and light that feels impossibly dramatic. If the moon were slightly larger or closer, eclipses would be more frequent but less stunning, with the corona hidden for longer. If it were slightly smaller or farther away, we would only ever see annular eclipses, where a ring of blinding sunlight remains visible around the dark silhouette of the moon, never the profound daytime darkness of totality. The odds of this precise alignment occurring on a life-bearing planet are astronomically small. Consider the countless moons orbiting planets in our own solar system, none of which share this perfect match with their parent star. Consider the vast number of exoplanets we have discovered, where such a configuration would be a staggering rarity, and yet, here we are. This coincidence has done far more than provide a beautiful show. It has fundamentally shaped human history. The predictable, yet awe-inspiring, drama of a total eclipse cracked open the door to science. Ancient astronomers, by predicting these events, demonstrated that the heavens operated by knowable rules, not just capricious gods. The eclipse became a tool for discovery, allowing scientists to confirm Einstein's theory of general relativity, study the sun's atmosphere, and understand orbital mechanics. Culturally and mythologically, the event is universally profound, interpreted across civilizations as a moment of cosmic conflict, a divine omen, or a temporary death and rebirth of the sun. So, we are left with a deeply personal mystery. Is this perfect celestial choreography, happening right in our own sky, merely a happy accident over 4 billion years in the making? Or does it hint at something more, in a universe filled with fine-tuned numbers and eerie alignments? The fact that our planet's companion provides such a perfect mask for our star feels like a signature, a piece of art placed deliberately in the one location where it could be seen, understood, and wondered at by conscious beings. That perfect alignment in our sky suggests a hidden order, a pattern we instinctively feel must exist. For centuries, astronomers looked at the solar system and saw not just planets, but a puzzle of placement. Why were the worlds spaced as they were? In the 1700s, a strange mathematical curiosity emerged, a pattern so simple it seemed too good to be true. It began as a footnote by a Prussian astronomer named Johann Titius, later popularized by his colleague Johann Bode. It became known as the Titius-Bode law. The rule was straightforward: start with a sequence of numbers, 0, then 3, then 6, then 12, doubling each time, add 4 to each number, then divide by 10. The results gave a startlingly accurate prediction of the average distances of the planets from the Sun, measured in astronomical units, where Earth is 1. Mercury fit at 0.4, Venus at 0.7, Earth at 1.0, Mars at 1.6, then there was a gap at 2.8, Jupiter fell perfectly at 5.2, and Saturn at 10.0. The gap was a mystery, a blank space in the pattern screaming for a missing world. When William Herschel discovered Uranus in 1781, its orbit of 19.2 astronomical units matched the law's next prediction almost perfectly. This success sent shockwaves through the scientific community. The hunt was on for the missing planet at 2.8. Astronomers scoured the heavens, and in 1801, they found something. Not a planet, but a tiny world named Ceres, orbiting right in that predicted gap. Soon, they found more small bodies there, revealing the asteroid belt. The law appeared prophetic. It felt like a fundamental secret of the solar system, a divine geometric plan written into the architecture of our cosmic neighborhood. But science advances. With the discovery of Neptune, the spell broke. Neptune's orbit did not fit the neat pattern. Pluto, later found, fit even worse. The Titius-Bode law was relegated to the status of a numerical coincidence, a curious trick of arithmetic with no known physical mechanism to back it up. It was discredited, a historical footnote of a time when we saw patterns in the noise. Yet, the story does not end there. The eerie predictive success of this simple pattern haunts us because it points to a deeper truth. While not a law of nature, it may be a shadow of one. Modern dynamics reveals that planets do not form in random locations. They emerge from the protoplanetary disk, and through gravitational interactions, they often settle into stable, semi-regular spacing. They push each other into orbits that avoid close encounters, creating a kind of natural harmony. We see this in the phenomenon of orbital resonance, where planets or moons orbit in simple integer ratios, like Jupiter's moons Io, Europa, and Ganymede, which orbit in a precise 1:2:4 ratio. These resonances create stability and clear gaps, much like the asteroid belt's location between Mars and Jupiter. So, while the specific numbers of the Titius-Bode law are a coincidence, the idea of patterned spacing is not. It is a statistical echo of the underlying dynamical processes that sculpt planetary systems. The law's success was a lucky guess that tapped into a real, but more complex, tendency for order to emerge from chaos. It reminds us that sometimes our search for simple patterns can accidentally brush against a profound, underlying truth, a truth written not in clean numbers, but in the gentle, relentless push and pull of gravity over billions of years. The search for patterns in our own solar system inevitably leads our gaze outward, to the staggering ocean of stars beyond, and here we confront not a pattern of alignment, but a pattern of absence, a cosmic silence so profound it has its own name. The physicist Enrico Fermi famously captured it in a simple, devastating question: where is everybody, given the sheer scale of the universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, many of which host planets? The numbers scream that life should be common. The Milky Way alone is over 13 billion years old, more than enough time for intelligent civilizations to arise, spread, and fill the galaxy. Even at a small fraction of light speed, a species could colonize the entire Milky Way in a few tens of millions of years, a mere blink in cosmic time. And yet, when we listen, we hear nothing. No signals, no probes, no megastructures dimming stars. The universe appears eerily, hauntingly quiet. This is the Fermi paradox, and it presents us with a coincidence of staggering proportions. The coincidence is not that we exist, but that we seem to be alone. Statistically, the silence is deafening. One powerful way to frame this eerie quiet is the concept of the Great Filter. Imagine the evolution of life from simple chemistry to a galaxy-spanning civilization as a series of colossal hurdles. The Great Filter is the idea that one of these steps is extraordinarily, perhaps almost impossibly, difficult to pass. It is a bottleneck so severe that it explains why the cosmos is not teeming with intelligence. The terrifying implication lies in the timing. Is the Great Filter behind us? This is the optimistic, yet humbling, view. It suggests that the step from non-living matter to simple, replicating life, or perhaps from simple life to complex, intelligent life, is a freak accident of cosmic rarity. Maybe the chain of events that led from stellar nucleosynthesis to DNA to conscious beings is so improbable that we are a singular miracle in a vast, empty galaxy. Our existence is the fluke, and the silence is simply the sound of a universe where such miracles almost never happen, but there is a darker, more chilling possibility. What if the great filter lies ahead of us? This hypothesis suggests that the step from an advanced technological civilization to a stable, enduring, galaxy-colonizing one is the true bottleneck. Perhaps every civilization, upon reaching a certain technological threshold, inevitably destroys itself through war, ecological collapse, or some unforeseen technological catastrophe. Or maybe they encounter something else, something lurking in the dark between the stars. In this scenario, the silence is a warning. The stars are empty not because life cannot arise, but because it cannot survive its own maturity. We look out at the quiet heavens and wonder if we are listening to a graveyard, or if we are simply the first to arrive at the party. This profound cosmic coincidence, the mismatch between our expectations of a noisy, crowded universe and the reality of a silent one, forces us to confront our own place in a deeply ambiguous cosmos. Are we a precious rarity, or are we simply early? The profound silence of the cosmos makes the rare moments when it seems to break all the more electrifying. One such moment arrived on a quiet Ohio night in August of 1977. An astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University, part of the ongoing search for extraterrestrial intelligence. The telescope slowly scanned the sky, listening for any signal that stood out from the natural radio hiss of the universe. What Amon saw printed on the readout stopped him cold. A column of alphanumeric data showed a sequence of numbers and letters representing signal strength. For 72 seconds, one channel had spiked with an intensity so powerful it overwhelmed the scale. In the margin, Amon circled the sequence and wrote 3 letters that would become legendary: WOW. The wow signal was born. This was not random noise. It possessed the precise hallmarks scientists had predicted for a genuine artificial signal from beyond Earth. It was a narrowband signal, concentrated on one specific frequency, 1.42 GHz. In nature, radio emissions from stars and gas clouds are broadband, smeared across a wide range of frequencies. A narrow, focused signal is the technological fingerprint of a transmitter. Even more compelling, this frequency falls within a protected band called the hydrogen line, a quiet channel in the radio spectrum that scientists had long suggested would be a logical calling card for any civilization trying to be heard. It is the natural emission frequency of the most common element in the universe, a universal landmark. For those 72 seconds, the signal rose in intensity as the telescope's beam swept onto it, peaked perfectly, and then faded away as the beam moved on, exactly as expected for a distant, fixed-point source. The signal appeared to originate from a region near the star cluster Chi Sagittarii, in the constellation Sagittarius, toward the crowded center of our own Milky Way galaxy. The discovery ignited a firestorm of hope and speculation. This was it, the moment humanity had dreamed of, a shout in the dark that seemed too perfect to be anything but a greeting. And then, nothing. Despite decades of repeated, targeted searches by telescopes around the world, the wow signal was never heard again, not a whisper, not an echo. It was a single, brilliant flash in the cosmic night, here and gone. This vanishing act is what transforms the signal from a potential discovery into a profound cosmic coincidence. The parameters were perfect, textbook even, for an intelligent transmission, yet its one-off nature defies explanation. If it was a deliberate beacon, why was it not repeating? If it was an accidental burst from an alien civilization, What phenomenal event could produce such a clean, powerful, and brief signal? All natural explanations have fallen short. It was not a passing satellite or aircraft, as those move and would have left a different signature. It was not likely a reflected signal from Earth, as that frequency is internationally guarded against terrestrial transmission. Some have proposed a comet, but the specific comets suggested were not in that part of the sky at that time, so we are left with a haunting possibility balanced on a knife's edge. The WOW signal remains, to this day, the strongest candidate for a potential extraterrestrial transmission ever detected. It is a coincidence of terrifying perfection, a message that fits the envelope of our expectations so neatly it feels like a cosmic test. Did we just miss our one chance to make contact, a beacon that flashed for a minute and then went silent forever? Or was it a bizarre, once-in-a-universe natural phenomenon that, by pure chance, mimicked the very signal we were hoping to find? In a silent universe, the WOW signal is the echo that never came back, a mystery that reminds us how desperately we want the silence to be broken, and how chilling it is when it almost is. The haunting silence following the WOW signal left us listening for a whisper, any whisper, from the cosmos. But sometimes, the universe does not speak in radio waves. Sometimes it speaks in motion, a faint, persistent tug felt by two lonely travelers on the edge of forever. They were called Pioneer 10 and Pioneer 11. Launched in the early 1970s, these robotic explorers were triumphs of human engineering, the first spacecraft to visit Jupiter and Saturn before embarking on a one-way journey into interstellar space. For decades, as they sailed farther from the Sun than any human-made object had ever gone, scientists meticulously tracked their trajectories using the Deep Space Network, a system of giant radio antennas. By measuring the precise Doppler shift in their radio signals, teams at NASA could calculate their speed and position with incredible accuracy, and that is when they found the anomaly. Something was wrong. Both Pioneers, now billions of miles from home, were slowing down just a little bit more than they should have been. According to Newtonian gravity, once you escape the major pull of the Sun and planets, your outward speed should be nearly constant, decreasing only by the tiny, predictable amount caused by the Sun's distant gravity. But the Pioneers were experiencing an additional, tiny deceleration. It was as if an invisible hand was reaching out from the direction of the Sun, applying a gentle but constant brake. This minuscule force was equivalent to about 10 billion times weaker than the gravity we feel on Earth's surface. To visualize it, imagine the Pioneers racing away at over 30,000 miles per hour. This anomaly was like having a single sheet of notebook paper gently pressed against their direction of travel. Tiny, yes, but over the vast distances and decades of flight, it added up to a positional error of hundreds of thousands of miles. For years, this Pioneer anomaly was a profound mystery. It was a signal in the data, a cosmic coincidence that seemed to whisper of new physics. Could it be evidence that our understanding of gravity itself was incomplete at these vast, interplanetary scales? Some theorists proposed modifications to Einstein's theory of general relativity. Others wondered if it was a hint of dark matter's gravitational influence in our solar system, or perhaps an effect of the spacecraft interacting with the solar wind in an unknown way. The anomaly became a tantalizing clue, a potential crack in the foundation of modern physics, all measured in the faint radio heartbeat of two distant probes. The mystery persisted for over 2 decades, a ghost in the machine of celestial mechanics. The solution, when it finally came, was not a revolution in physics, but a masterclass in humility. It was heat not from the sun, but from the spacecraft themselves. The pioneers were powered by radioactive thermoelectric generators, which produced electricity from the decay of plutonium. This process also generated a significant amount of waste heat. That heat radiated away from the spacecraft in all directions, but critically, the pioneers were designed with their dish-shaped antennae always pointed back toward Earth, and thus generally back toward the Sun. This meant more heat was radiating from the back of the spacecraft, the side facing the Sun and Earth, than from the front. Photons of infrared radiation carrying that heat away also carry a tiny amount of momentum. The uneven radiation created a tiny net pressure, an invisible photon breeze pushing against the direction of travel. It was the spacecraft's own warmth, gently but relentlessly, slowing them down. Once engineers built exquisitely detailed thermal models of the pioneers, accounting for every watt of power and every surface's reflectivity. The anomaly vanished. The numbers matched, the ghost was explained, yet the legacy of the pioneer anomaly is far more than a solved engineering puzzle. It stands as a perfect example of a cosmic coincidence that was not cosmic at all, but profoundly human. For years, the data pointed unequivocally to something unknown. It perfectly mimicked the signature of new physics, a deviation from the known laws of the universe. It was a siren song that led some of the brightest minds down paths of radical theory. Its eventual explanation in mundane thermal effects is a powerful reminder of a fundamental truth in our exploration of the cosmos. The universe is under no obligation to be obvious. The most tantalizing clues can emerge from our own blind spots, from the subtle, second-order effects we overlook in our grand models. The pioneer's journey taught us that sometimes the whisper from the edge of space is not the voice of a new law, but the echo of our own machinery, a reminder to check our work with relentless, humble precision before we declare a revolution. The phantom tug on the Pioneer probes was traced to a whisper of their own heat, a lesson in our own blind spots. Yet another, even stranger motion persists, one that happens not in the deep void, but in our own backyard during moments of celestial precision. When engineers plot a course to the outer planets, they often use a clever trick called a gravity assist. The idea is to steal a tiny fraction of a planet's orbital momentum. A spacecraft approaches a planet from behind, swings around it, and gets slingshotted forward, like a roller coaster car catching a boost from a descending slope. The math for these maneuvers is exquisitely precise, a ballet of orbital mechanics timed down to the second. But sometimes, the spacecraft gains a tiny, unexpected extra kick. Or it loses a bit more speed than predicted. These are the flyby anomalies, and they are maddeningly inconsistent. The Galileo spacecraft, on its way to Jupiter, performed an Earth flyby in December 1990. As it whipped around our planet, tracking data showed it had gained about 4 millimeters per second more velocity than the models said it should have. That is an almost imperceptible amount, less than the speed a snail crawls. But in the world of deep space navigation, where a millimeter per second error over years translates to being thousands of miles off target, it is a glaring red flag. The Rosetta Comet Chaser experienced a similar anomaly during its Earth flyby in 2005 and again in 2007. The Near-Shoemaker probe, heading to an asteroid, showed one as well. Each time, the discrepancy was minute, but undeniably present in the pristine radio tracking data. The strangest part is the pattern, or seeming lack of one. The effect does not appear to be a simple constant. Intriguingly, some scientists analyzing the data noticed a potential link to Earth's rotation. The anomaly's size seemed to vary depending on whether the spacecraft flew over the equator or at an angle, and whether its closest approach happened on the day side or the night side of the planet. It was as if the spinning Earth itself was imparting an extra, uncalculated nudge, a ghostly hand on the spacecraft's shoulder as it passed. For years, this has been a classic unsolved problem in astrodynamics. Is it an unaccounted-for effect of our planet's uneven gravity, its lumpy geoid? Could it be subtle atmospheric drag at extremely high altitudes, or an interaction with Earth's magnetic field? Perhaps it is a tiny error in how we model the Doppler effect for signals traveling through Earth's atmosphere. Each proposed explanation has struggled to fit all the flyby data perfectly. The coincidence here is not just that the anomalies happen, but that they appear to correlate with our planet's orientation and spin. This suggests the cause is local, something about Earth itself that our physics models are missing by a hair's breadth. Yet, after decades and numerous flybys, a definitive, universally accepted answer remains elusive. The flyby anomaly stands as a quiet testament to a humbling truth. Our mastery of orbital mechanics is incredible, but not yet perfect. In the precise choreography of a gravity assist, a step we think we invented, the universe seems to be adding a faint, improvisational flourish of its own. This gentle, unexplained nudge during planetary flybys is a puzzle on a human scale, but the solar system holds a boundary on a scale so vast it defies our models. Far beyond the orbit of Neptune, in the cold, dark reaches where sunlight is a faint memory, lies a ring of icy debris known as the Kuiper Belt. This is the solar system's attic, a frozen archive holding pristine leftovers from the dawn of our planetary system. Astronomers expected this belt to be a gradually thinning field of icy worlds, slowly fading into the interstellar void, but what we found instead is a wall. Observations reveal a sudden, dramatic drop in the number of objects beyond a distance of about 50 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, so we are talking about a region roughly 50 times farther out than our own orbit. This boundary is so sharp it has been named the Kuiper Cliff. It is as if you were walking through a forest that abruptly ends at a straight, clean edge, with nothing but empty plains beyond. According to our best models of how the solar system formed, this should not happen. The primordial disk of dust and gas that birthed the planets extended much farther out. We should see a populous belt of icy bodies, perhaps thinning gradually, but certainly not ending in such an abrupt precipice. So what carved this cliff edge in the deep freeze of space? One compelling hypothesis involves a violent past, billions of years ago, when the Sun was young and still nestled in its stellar nursery. Another star may have passed uncomfortably close to our infant solar system. This stellar intruder's gravity could have acted like a cosmic rake, stripping away the outer material of the Kuiper Belt and stealing it into interstellar space, leaving behind the sharp edge we see today. It is a dramatic story, a celestial robbery that shaped our system's frontiers. Another, even more tantalizing idea points to a presence, not an absence. Could the gravity of an unseen, massive planet, far beyond Pluto, be shepherding the Kuiper Belt objects, clearing out a region beyond its orbit? This is the core of the Planet 9 hypothesis. A hypothetical world, several times the mass of Earth, on a distant, elongated orbit, could explain not only the Kuiper Cliff, but also the peculiar, clustered orbits of some extreme trans-Neptunian objects. Its gravitational influence would act as a border guard, pushing debris inward and creating that stark boundary. Then there is the possibility that the cliff is a fossil, a relic of the solar system's very formation. Perhaps the original protoplanetary disk itself had a sharp outer edge, maybe truncated by the gravitational influence of a nearby massive star in the birth cluster, or maybe because the materials simply ran out at that distance. In this view, the Kuiper Cliff is not something that happened to the belt, but the belt's original, preserved shape. Each explanation carries its own profound implications. A passing star reshuffles our cosmic neighborhood's history. An unseen planet redefines the solar system's map. A primordial edge speaks to the specific conditions of our sun's birth. The coincidence lies in the location itself, that 50 astronomical unit mark. It is a clean, round number that stands as a silent sentinel at the edge of the known. We do not yet know which story is true, or if the answer is something we have not yet conceived. But the Kuiper Cliff is a stark reminder that even our own celestial backyard, a place we think we understand, holds borders we cannot explain, boundaries written in ice and darkness that challenge the story we tell ourselves about home. Beyond that sharp Kuiper Cliff, the solar system does not simply end. It dissolves into a ghostly, spherical haze of frozen relics, a place so distant and faint we have never seen it directly. This is the Oort cloud, a hypothesized shell of icy planetesimals beginning roughly 2,000 astronomical units from the Sun and stretching perhaps halfway to the nearest star. Its existence is not a wild guess, but a necessary inference. Every so often, a spectacular visitor streaks through the inner solar system, a comet with a tail that stretches across the sky. These are the long-period comets, taking tens of thousands or even millions of years to complete a single orbit. Their paths are not confined to the flat plane of the planets, but arrive from any direction, tracing back to a vast, spherical reservoir. The Oort cloud is that reservoir, the ultimate source of these primordial icebergs, and its relationship with the galaxy at large is a masterpiece of delicate timing. The objects in the Oort cloud are so far out that the Sun's gravitational grip is tenuous, a whisper against the background hum of the galaxy itself. They exist in a state of frozen suspense. Here lies the coincidence. The gentle, persistent gravitational tides of the Milky Way itself, combined with the occasional close passage of a wandering star, act as a perfect trigger. These galactic forces are neither too strong nor too weak. They are exquisitely poised to give just enough of a nudge, like a careful hand shaking a tree laden with fruit. The galactic tide and passing stars perturb the orbits of these dormant icy bodies. A slight gravitational shove at just the right point in an object's slow orbit can alter its path, sending it tumbling down the Sun's gravity well on a new, plunging trajectory. Without this external influence, the Oort cloud would remain a silent, frozen archive, and comets would rarely visit the warmth of the inner solar system. But if the galactic environment were more violent, if stellar passes were more frequent or the galaxy's tidal forces stronger, the Oort cloud would be stripped away entirely, scattered into interstellar space. Instead, we live in a Goldilocks zone of galactic dynamics. The Milky Way's gravity and the sparse traffic of stars provide just the right amount of disturbance to maintain a steady, gentle rain of comets over billions of years. This cosmic coincidence has profound implications. These icy messengers from the outermost dark may have been the delivery vehicles for water and organic compounds to the early Earth, seeding the ingredients for life. They are also potential agents of change, with impacts capable of altering climates and shaping biological history. The beautiful, terrifying spectacle of a comet blazing across our sky is not a random accident. It is the end result of a perfect balance, a distant shell of ice trembling at the faint touch of the entire galaxy, sending frozen time capsules inward on a journey that culminates in a brief, brilliant flash of light against our night. Our solar system's position is a quiet suburban street in a vast and dangerous metropolis. The Milky Way is a swirling disk of 100 billion stars, but it is not uniformly hospitable. Just as a planet can have a habitable zone where liquid water is possible, a galaxy can have a galactic habitable zone, a region where conditions are just right for complex life to arise and persist. We are not in the bustling downtown, nor are we in the isolated, empty countryside. We are in the quiet, stable suburbs, and that is no accident. The dangers begin at the galactic core. Nestled, there is a supermassive black hole, Sagittarius, a star, surrounded by a dense cluster of stars. The radiation from this energetic core is intense, with high-energy X-rays and gamma rays that could sterilize planets or strip away atmospheres. The sheer density of stars also increases the risk of catastrophic close encounters, gravitational disruptions that could fling a planetary system into the void or trigger devastating comet showers. Too close to the center, and the environment is far too violent for life to gain a stable foothold over billions of years. On the other hand, the far outer reaches of the galactic disk present a different problem. Here, stars are made from material that has been recycled fewer times. They have lower metallicity, a term astronomers use for elements heavier than hydrogen and helium. These heavier elements, forged in the hearts of stars and scattered by supernova, are the essential building blocks for rocky planets like Earth. A star system born in the metal-poor outskirts might lack the raw materials to form terrestrial planets at all, leaving only gas giants or barren worlds. Our Sun, with its rich composition of metals, formed in a region that had been seeded by generations of earlier stars, but location is more than just a radial address. We also reside in a relatively quiet spiral arm, the Orion Spur, nestled between the larger Perseus and Sagittarius arms. Spiral arms are waves of density, regions where star formation is triggered as the galaxy rotates. While they are beautiful, they are also turbulent nurseries full of young, massive, and short-lived stars that explode as supernova. If our solar system were embedded deep within a major spiral arm, the frequency of nearby supernova explosions would be significantly higher, potentially wiping out complex life with sterilizing radiation every few million years. Our position on a minor spur gives us a measure of protection, a quieter neighborhood with fewer catastrophic stellar events. Even our orbit around the galactic center is remarkably stable and circular, avoiding wild swings that would take us through more dangerous regions. The confluence of these factors, our distance from the core, our placement in a quiet spiral feature, our solar system's metallicity, and our orbital stability, defines a narrow galactic sweet spot. It is another layer of the cosmic coincidence problem. For a planet to host observers, it must not only orbit its star at the right distance, but its star must also orbit the galaxy at the right distance, in the right neighborhood, at the right time in cosmic history. We find ourselves in that precise and privileged zone, a safe harbor in a galaxy that is, for the most part, a spectacularly dangerous place. Our safe galactic suburb offers a stable platform for life, but stability alone is not enough. It also requires timing, and the moment humanity opened its eyes to the cosmos was a moment of breathtaking cosmic luck. To understand just how lucky, you must compress the entire history of the universe into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. Our Milky Way galaxy forms in early March. The solar system and Earth coalesce in early September. Simple life appears on our planet by late September. Dinosaurs rule the Earth in late December. They go extinct at about 9:45 in the evening on December 30th. All of recorded human history, from the first cities to the internet, from the pyramids to the present day, unfolds in the last 30 seconds of the entire year. December 31st, 11:59 and 30 seconds. We are a cosmic afterthought in terms of duration, but in terms of perspective, our arrival is perfectly, suspiciously timed. For billions of years after the Big Bang, the universe was a fog. This was the cosmic dark ages, a time when space was filled with a dense soup of neutral hydrogen gas that scattered light, making it utterly opaque. No stars, no galaxies, nothing was visible across the vastness. It was a universe with no view. Then, around the 380,000-year mark, the fog lifted. The first stars ignited, their fierce ultraviolet radiation slowly reionizing the hydrogen, clearing the haze and making the universe transparent. This process took hundreds of millions of years. By about 1 billion years after the Big Bang, the cosmos had become largely clear, a dark, sparkling expanse. Now, fast forward to the future. The universe's expansion is accelerating, driven by that mysterious dark energy. As it accelerates, distant galaxies are being carried away from us faster and faster. There will come a time, tens of billions of years from now, when every galaxy beyond our own local group will have been pushed so far away that their light can no longer reach us. They will redshift into invisibility, disappearing beyond an event horizon. The universe will become a lonely island, a solitary cluster of galaxies in an infinite, black, and unknowable void. The window for a clear view of the cosmos is not infinite. It opened about 13 billion years ago and will begin to close in the distant, but finite, future. And here we are, conscious beings with powerful telescopes, emerging almost exactly in the middle of this brief window of cosmic transparency. We arrived after the fog cleared, giving us a pristine view of the cosmic microwave background, the ancient galaxies, and the large-scale structure of the universe. But we also arrived before the Great Vanishing, while the light from most of creation is still streaming in, allowing us to map the cosmos and deduce its history and fate. This is a staggering coincidence. If humanity had evolved just a few 100 million years earlier, our night sky would have been a featureless, glowing fog. If we emerge hundreds of millions of years in the future, our descendants will see a far emptier sky, having lost the evidence needed to ever piece together the story of the Big Bang and the expanding universe. Their cosmology would be based on a tiny, local sample, forever ignorant of the grand cosmic drama. So, are we special? One answer is the anthropic principle again. Observers can only arise when conditions allow for observation. We find ourselves in the clear window because that is the only time a civilization can find itself. It is a selection effect, not a design, but another perspective is more haunting. It suggests that if intelligent life is common in the universe, we should see evidence of civilizations that arose billions of years before us. During the many billions of years, the window has been open. Their activities, their signatures, should be everywhere, yet we see none. This brings us back to the Great Filter and the Fermi paradox. our perfectly timed emergence might not signal a privileged position, but a terrifying rarity. Perhaps civilizations like ours are so improbable that they only ever arise once in a great while, in this narrow sliver of cosmic time, blinking into existence just in time to see the grandeur before the curtain falls, alone in a theater built for an audience that never arrived. Our emergence in the clear cosmic window feels like a profound piece of timing, but the coincidences are not just about when we look. They are woven into the very numbers that define reality. Some of these numbers are not just fine-tuned, they are astronomically large, and they seem to be talking to each other across the chasm between the very small and the very large. This is the mystery of large number coincidences, and it begins with a physicist named Paul Dirac. In the 1930s, Dirac was pondering the fundamental constants of nature, the immutable numbers that govern the forces of physics. He looked at the ratio of the strength of the electromagnetic force, which holds atoms together, to the strength of gravity, which holds planets and galaxies together. The number he calculated was staggering, approximately 10 to the power of 40. That is a 1 followed by 40 zeros, an almost unimaginable scale. But then he looked at another enormous number, the age of the universe. When expressed in the fundamental unit of time known as the Planck time, the incredibly brief interval it takes light to cross a Planck length, the universe's age is also a number around 10 to the power of 40. It was a bizarre mirror. Two immense, seemingly unrelated numbers, one from the realm of particle physics and the other from cosmology, were roughly equal. Dirac did not think this was an accident. He proposed his large number hypothesis, suggesting that these enormous coincidences were clues that the fundamental constants might not be constant at all. Perhaps the strength of gravity, for instance, was slowly changing over the vast lifespan of the cosmos, in just such a way that these large ratios would remain linked. It was a radical idea that the laws of physics could evolve in tandem with the expanding universe. The coincidences do not stop there. Consider the number of protons in the observable universe, another colossal figure. Estimates place it around 10 to the power of 80. Intriguingly, that is roughly the square of 10 to the 40, the square of Dirac's large number. It is as if the universe's scale, its content, and its age are all bound together by a simple, silent arithmetic. So what are we to make of these numerical echoes? One possibility is that they are indeed meaningless, a kind of cosmic numerology. With so many large numbers floating around in physics and cosmology, some are bound to look similar purely by chance. We are pattern-seeking creatures, and we might be connecting dots that are not truly linked. Yet, the persistence and simplicity of these relationships are deeply unsettling to dismiss entirely. They feel too clean, too suggestive. The other, more profound possibility is that these coincidences are a genuine whisper from a deeper layer of reality. They hint that the micro-world of quantum forces and the macro-world of cosmic expansion are not separate domains, but are fundamentally intertwined. Perhaps there is a unifying principle, a theory of everything, that naturally produces these large numbers as a consequence of its mathematics, linking the birth of the universe to the strength of the forces within it. In this view, the age of the universe and the strength of gravity are two sides of the same coin, set at the moment of creation. We are left staring at a numerical signature that spans all of existence, a signature written in zeros, connecting the force that binds your atoms to the story of the cosmos itself. It is either a breathtaking clue or a magnificent mirage, and the answer depends on whether the universe is simply showing us numbers, or whether it is trying to teach us how to count. These vast numerical echoes seem to speak a language of pure mathematics, but one specific number, a precise resonance inside an atom, speaks directly to our own existence. The story begins not with a discovery, but with a stubborn problem and a physicist's sheer audacity. In the 1950s, Fred Hoyle was wrestling with a fundamental question. Where did all the carbon in the universe come from? We are carbon-based life forms. The complex molecules in our bodies are built around carbon chains. But according to the standard models of stellar nucleosynthesis, the process by which stars forge elements, carbon should be incredibly rare. Here is why. Inside a star, the first step is fusing hydrogen into helium. When the helium builds up, two helium nuclei, also called alpha particles, can fuse to form beryllium-8. But beryllium-8 is wildly unstable. It falls apart in a fraction of a second. For carbon to form, a third helium nucleus would have to slam into that fleeting beryllium-8 before it disintegrated. The problem was the odds. The calculations showed this three-way collision happened far too slowly and inefficiently to account for the immense abundance of carbon we see in the cosmos, and by extension, in ourselves. The numbers did not add up. Hoyle, however, was convinced the carbon was there, so the process had to work. He made a breathtaking leap of logic. He proposed that the carbon-12 nucleus itself must have a special property, what physicists call a resonant energy state. Think of it like this. Imagine trying to push a child on a swing. If you push at random times, you will not get them very high. But if you push in perfect rhythm with the swing's natural frequency, each small push adds energy, sending them soaring. Hoyle argued that inside a star, the energy released when beryllium-8 and a helium nucleus collided must exactly match a natural, resonant frequency of the carbon-12 nucleus. This resonance would act like a perfectly timed push, making the fusion reaction billions of times more efficient, a cosmic shortcut to building carbon. The staggering part was that this specific energy level had never been observed. Hoyle, an astronomer, walked into the nuclear physics laboratory at Caltech and told the experimentalists, led by Willie Fowler, that this resonance must exist. He gave them the exact energy it should be found at. To the physicists, this was an outrageous prediction from a theorist meddling in their field, but they checked. And there it was. The carbon-12 nucleus had a resonant state at precisely 7.65 million electron volts, exactly as Hoyle had predicted from the cosmic abundance of carbon alone. The coincidence here is so precise it is chilling. That specific resonance energy is a razor-thin window. If it were just a few percent higher, the reaction would not work, and carbon would be a cosmic rarity. If it were slightly lower, almost all the carbon produced would immediately fuse with another helium nucleus to form oxygen, leaving little carbon behind. The universe would be rich in oxygen, but devoid of the versatile backbone of organic chemistry. Life as we know it would not exist. This is not a minor adjustment. It is a nuclear tuning of unimaginable precision, a setting on the atomic scale that directly enables planets, trees, and conscious minds, so we are forced to ask the same haunting question. Was this resonance, this perfect atomic harmony, simply a random roll of the quantum dice? Or does the fact that we can deduce its existence from the mere presence of life in the cosmos suggest something deeper, a universe where the laws of physics are not just life-permitting, but in this one critical instance, life-inviting? Hoyle himself, an atheist, was so shaken by the perfection of this coincidence that he famously remarked, "It appeared as if a super-intellect had monkeyed with the laws of physics." The carbon in your hands, the carbon in every living thing, is here because of a number that had to be exactly right, and miraculously, it was. The carbon resonance Hoyle predicted is not a solitary note, but the critical bridge in a stellar symphony known as the triple alpha process. Inside the fiery hearts of massive stars, a delicate and improbable dance unfolds, one that transforms the ashes of dead elements into the very stuff of life. It begins with helium, the element forged from hydrogen fusion. When a star exhausts its hydrogen, its core contracts and heats up, igniting helium fusion. The first step is for two helium nuclei, which physicists call alpha particles, to collide and fuse. This creates not carbon, but beryllium-8, and here lies the first hurdle. Beryllium-8 is catastrophically unstable. It exists for only about 1/10,000th of a nanosecond before it flies apart back into two helium nuclei. For carbon to form, a third helium nucleus must strike this fleeting, ghostly beryllium-8 nucleus in the vanishingly small window of time before it disintegrates. The odds are astronomically poor. It is like trying to throw a third playing card onto a house of cards made of two cards in the split second before they collapse, and expecting a stable pyramid to form. In a universe governed by simple probabilities, this reaction should be so slow and inefficient that carbon would be an exotic rarity, but our universe is not that simple. The miracle hinges on the precise energy levels of the atomic nuclei involved. When the beryllium-8 and the incoming helium nucleus meet, the total energy they bring to the collision is almost exactly equal to a specific, excited energy state of the carbon-12 nucleus. This is the Hoyle state, that resonant frequency. This perfect match changes everything. Instead of a messy, unlikely collision, the reaction becomes resonant, like a singer shattering a glass with the precise pitch that matches the glass's natural frequency. The energy fits perfectly, allowing the three helium nuclei to snap together into a carbon-12 nucleus with incredible efficiency. This resonance boosts the reaction rate by a factor of many billions, transforming a cosmic bottleneck into a prolific production line. Without it, stars would struggle to make carbon, and the universe would be devoid of its most versatile chemical element. But the coincidences do not end there. This resonant energy is a razor's edge. If it were just a little bit higher, the reaction would not work at all. If it were slightly lower, almost all the carbon produced would immediately fuse with another helium nucleus, creating oxygen instead. The process is balanced on a knife edge between failure and a runaway conversion that leaves no carbon behind. The fact that the resonance exists at just the right energy, in just the right place, to allow copious carbon to accumulate, is a piece of nuclear alchemy so precise it feels designed. This stellar forge, this triple alpha process, is the primary source of every carbon atom in your body, in every tree, and in every diamond. That carbon did not simply appear. It was forged in the heart of a dying star, through a chain of reactions so improbably fine-tuned that it allowed the universe to step across a chasm of instability and build the foundation for everything that came next. The carbon forged in stellar furnaces becomes the ink for a far more intimate story, one written in the chemistry of our own world. That story depends on a single, miraculous molecule. Water, it seems so ordinary, a simple combination of two hydrogen atoms and one oxygen atom. Yet, water is the most anomalous substance in the known universe. Its bizarre properties are not just interesting quirks, they are the non-negotiable prerequisites for life as we know it. This is the water anomaly, a cascade of coincidences so perfectly aligned it feels like a cosmic cheat code. Consider what should happen. When most liquids freeze, their molecules pack closer together, making the solid denser than the liquid. If water followed this rule, ice would sink. Ponds and lakes would freeze from the bottom up, becoming solid blocks of ice in winter, killing all aquatic life. Instead, water expands when it freezes. Ice floats. This single, defiant property creates an insulating layer on top of bodies of water, protecting the liquid ecosystem below through the coldest seasons. It also sculpts our planet, as expanding ice cracks rock to form soil. This anomaly stems from the hydrogen bond, a weak attraction between water molecules. In liquid water, these bonds are constantly forming and breaking, but when water freezes, the molecules arrange into a rigid, hexagonal crystal lattice held together by hydrogen bonds. This structure is surprisingly spacious, like a honeycomb with more air than wax. The result is that solid water takes up more space than liquid water, making it less dense. Then there is water's incredible capacity to store heat. It has one of the highest specific heat capacities of any common substance. This means it takes a tremendous amount of energy to raise its temperature. Our planet's vast oceans act as a global thermal buffer, absorbing heat during the day and releasing it slowly at night, moderating Earth's climate and preventing the wild temperature swings that would make complex life impossible. Water is also the ultimate solvent, the universal dissolver. Its polar nature, with a slightly positive end and a slightly negative end, allows it to pry apart ionic compounds like salts and surround other polar molecules. This solvent power is why water can carry nutrients into cells, flush out waste, and facilitate the countless chemical reactions of metabolism. Blood, sap, and cytoplasm are all water-based solutions, the rivers of life flowing through every organism. The profound coincidence is not that water has these properties, but that all of these anomalous properties manifest precisely within the narrow band of temperature and pressure found on the surface of our planet. Water is a liquid between 0 and 100 degrees Celsius at sea level, a range that brackets Earth's average surface temperature perfectly. Its high boiling point means it remains a liquid over most of our world, rather than evaporating instantly into a vapor. Its expansion upon freezing happens right at the freezing point we commonly experience. Its peak density occurs at 4 degrees Celsius, which is why deeper water in lakes stays at this temperature, again protecting life. If Earth were slightly colder or hotter, or if atmospheric pressure were different, water's life-giving anomalies might be shifted outside the conditions of our environment, rendering them useless. So, is water uniquely fit for life, or is our perspective hopelessly narrow? Could other solvents, like liquid methane on Titan or sulfuric acid in Venusian clouds, support a different kind of biochemistry in a different cosmic environment? It is a fascinating thought experiment. Ammonia, for instance, also forms hydrogen bonds and remains liquid at much colder temperatures. Perhaps in the frigid seas of an ice moon, an ammonia-based biology could evolve. Yet, water possesses a combination of traits that appear unmatched. Its stability, its solvent range, its role in the chemistry of carbon-based molecules like proteins and DNA create a synergy that seems extraordinarily potent for fostering complexity. The water anomaly presents us with a choice. We can see it as another staggering piece of fine-tuning, a molecule whose every oddity conspires to cradle life on a planet like ours. Or we can see it as a reminder that life may be more inventive than we can imagine, capable of using whatever chemistry a world provides. But for us, here and now, the miracle is that the most common liquid in our world is also the most strangely, suspiciously perfect one. The water that cradles life depends on a steady source of warmth, a star that has burned with remarkable consistency, but our sun has a secret, one that should have doomed our planet before life ever began. According to the well-understood physics of stellar evolution, the young sun was significantly dimmer. When our solar system first formed, the sun burned at only about 70% of its current brightness. For billions of years, it slowly grew warmer as nuclear fusion built up a core of helium ash. This presents a catastrophic problem for Earth's early history. Basic climate models tell us that with a sun that faint, our planet's average temperature should have been well below freezing. The entire world should have been a global icehouse, a gleaming snowball locked in a permanent deep freeze. The geological record, however, tells a completely different story. The oldest rocks on Earth, some dating back over 3.8 billion years, show clear evidence of liquid water. There are sedimentary formations, ripple marks, and minerals that can only form in the presence of flowing water. Even more compelling, the fossil record places the earliest known life forms, simple microbial mats, in this same ancient era. The Earth was not frozen. It was wet, warm, and alive. This glaring contradiction is the faint young sun paradox, a puzzle that has haunted climatologists and planetary scientists for decades. How did our planet defy the laws of physics and stay warm under a cold sun? The answer lies not in the star, but in the intricate, dynamic system of the planet itself. Earth's climate did not passively receive sunlight, it actively compensated. The leading explanation points to a powerful planetary thermostat, a greenhouse effect far stronger than today's. In its youth, Earth's atmosphere was likely rich in potent greenhouse gases like methane and, especially, carbon dioxide. Volcanic activity was rampant, constantly venting carbon dioxide into the air. Without plants or weathering processes to quickly draw it down, this carbon dioxide could have built up to concentrations hundreds of times higher than present levels. This thick, insulating blanket would have trapped enough of the sun's feeble heat to keep the oceans liquid. It was a perfect, if precarious, balance. As the sun slowly grew brighter over the eons, the planet's thermostat had to adjust. Here, another remarkable feedback mechanism likely came into play: the carbonate-silicate cycle. In simple terms, carbon dioxide in the atmosphere dissolves in rainwater, forming a weak acid that weathers rocks on land. This weathering pulls carbon dioxide out of the air, washing the minerals into the oceans, where they eventually form carbonate rocks like limestone, locking the carbon away. The fascinating part is that this weathering process runs faster when the planet is warmer. So, as the sun grew brighter and threatened to overheat the Earth, the increased temperature sped up rock weathering, pulling more carbon dioxide out of the atmosphere, which cooled the planet back down. Conversely, if things cooled too much, weathering would slow, allowing volcanic carbon dioxide to build up and warm the planet again. It is a self-regulating, billion-year-long dance. The staggering coincidence is that this delicate balancing act worked, and worked perfectly, for over 4 billion years. The initial conditions, the composition of the early atmosphere, the presence of active geology and liquid water to drive the cycle, all aligned to create a stable climate buffer against a changing star. It suggests that habitability is not a static condition, but a dynamic process, a planet learning to regulate its own fever. Yet the paradox deepens when we consider the margins. Some climate models indicate that even with a strong greenhouse effect, the early Earth was skating dangerously close to the edge of global glaciation. A slight nudge in atmospheric composition, a different continental arrangement, or a slightly weaker volcanic outgassing rate, and the Great Freeze would have begun, potentially becoming irreversible. We avoided that fate. The fact that our planet not only possessed the right ingredients for a thermostat, but that those ingredients were mixed in precisely the right proportions across geological time, feels like more than luck. It feels like a system that was tuned, from the very beginning, to preserve the possibility of a blue marble in space, a world determined to stay alive under a cold, young sun. That delicate planetary thermostat is just one piece of a much larger, more improbable puzzle. When you step back and look at the entire list of requirements for a world like ours, the notion of a common, life-filled galaxy begins to crumble. This is the core of the rare Earth hypothesis, a sobering argument that complex, multicellular life may be an astonishing cosmic rarity. It is not enough to be in the right place around the right star. A planet must win a relentless series of lotteries, each one dependent on the last. Start with the star itself. Our Sun is a stable, long-lived G-type main sequence star. It is not part of a binary or multiple star system, which would create chaotic, unstable orbits for planets. It also avoids the violent flares and radiation outbursts common to smaller, dimmer red dwarf stars, which would periodically sterilize the surfaces of any orbiting worlds. Our Sun is, in a cosmic sense, remarkably boring and predictable, providing a steady stream of energy for billions of years. Then there is our location within the galaxy, that quiet suburban spiral arm we discussed, safe from the radiation of the core and the chaos of dense star clusters. But the coincidences truly accumulate when we focus on Earth itself. Our planet is a rocky world of just the right size and composition. It is large enough to retain a substantial atmosphere and maintain internal heat for geological activity, but not so massive as to become a gas giant with a crushing, toxic atmosphere. That internal heat drives plate tectonics, the slow, grinding dance of continental plates. This is not just a geological curiosity, it is a global recycling system. Plate tectonics regulates carbon dioxide levels through the weathering of rocks, preventing a runaway greenhouse effect like the one that scorched Venus. It also recycles minerals and nutrients essential for life, constantly refreshing the planetary surface. Without this process, a planet would likely become geologically dead and climatically unstable. Another non-negotiable shield is our planet's magnetic field, generated by the churning of molten iron in Earth's outer core. This invisible force field deflects the solar wind, a constant stream of charged particles from the Sun. Without this magnetic shield, this solar wind would slowly but surely strip away our atmosphere, as it did on Mars. It also protects the surface from harmful cosmic and solar radiation, allowing life to thrive on land and in shallow seas. Look outward, and more guardians appear. Our solar system contains a giant planet, Jupiter, orbiting in just the right place. Its immense gravity acts as a cosmic vacuum cleaner, deflecting and capturing many comets and asteroids that would otherwise bombard the inner planets with catastrophic frequency. While impacts can deliver water and organic compounds, too many would prevent life from ever gaining a foothold. Jupiter provides a stable, protective influence. Then there is our oversized moon. As we have seen, Its perfect alignment creates eclipses, but its gravitational influence does something far more vital. It stabilizes the tilt of Earth's rotational axis. Without the Moon's steadying hand, Earth's axial tilt would wobble chaotically over time, driven by the gravitational tugs of the Sun and other planets. This would cause wildly erratic and extreme climate shifts, making the long-term stability needed for the evolution of complex life nearly impossible. Our Moon is a planetary gyroscope, ensuring relatively mild seasons for eons. Even Earth's large supply of water, delivered by ancient comet impacts, is a matter of chance. Too little water, and you have a desert world. Too much, and you have a global ocean with no continents to provide mineral nutrients and shallow, sunlit seas where photosynthesis could evolve. Earth found a perfect balance between land and sea. When you add it all up, the list is staggering. A stable, solitary star, a safe galactic neighborhood. A planet of the right size and composition, plate tectonics, a strong magnetic field, a giant planetary guardian, a large, stabilizing moon, the right amount of water. A circular orbit within the stellar habitable zone. Each of these factors is, by itself, perhaps not exceedingly rare, but the probability of all of them occurring together on a single world and persisting in a stable equilibrium for billions of years seems vanishingly small. The rare Earth hypothesis suggests that while simple microbial life might be common in the universe, the emergence of complex, intelligent, technology-building life requires such a specific and interconnected chain of cosmic coincidences that Earth may be extraordinarily special, a lonely oasis of complexity in a vast and silent cosmos. It transforms our planet from a potential example into a potential miracle, a single, fragile thread woven from a dozen different kinds of luck. That fragile chain of planetary coincidences exists within a universe whose structure is written in its oldest light, and there, on the largest canvas imaginable, another anomaly refuses to fade away. Among the subtle temperature variations of the cosmic microwave background, one feature stands out not for its subtlety, but for its stark, chilling presence. It is known simply as the cold spot. This is not a poetic name. It is a precise description of a region in the constellation Eridanus that is significantly colder than the surrounding sky. The temperature difference is minute, only about 70 microkelvins, but its scale is immense. The cold spot spans a staggering 1 billion light-years across. In a map of the primordial universe that is otherwise a nearly uniform tapestry of tiny fluctuations, this is a colossal bruise, a patch of shadow so vast it could swallow thousands of galaxies whole. Statistically, it is an extreme outlier. When scientists run simulations of the Big Bang based on our standard model of cosmology, they rarely, if ever, produce a feature this large and this cold purely by random chance. The probability of it being a simple statistical fluke is less than 2%. That means there is a 98% chance it is not a fluke, that it is telling us something real and profoundly strange about the structure of the cosmos. So what could create a cold patch on the baby picture of the universe? One explanation is almost as bizarre as the spot itself. It could be a cosmic texture, a defect in the fabric of space-time itself. In the frenzied moments of the universe's birth during the inflationary epoch, the fundamental fields that govern reality may have undergone phase transitions, like water freezing into ice. Sometimes, these transitions are not perfectly smooth. They can create tangled knots or textures in the very geometry of space. If such a texture existed within our observable universe, its immense gravitational energy would have left a distinct imprint on the cosmic microwave background, a specific kind of cold spot. Some theorists take this idea even further, suggesting the cold spot could be the scar from a collision with another universe during inflation, a bruise left by a reality that is not our own. These are breathtaking concepts, but they remain speculative, pushing the boundaries of known physics. A more conventional, though still extraordinary, explanation involves a staggering emptiness. If a truly vast supervoid, a region of space almost devoid of galaxies and dark matter, lies between us and the cold spot, it could create the cold signature through an effect called the integrated Sachs-Wolfe effect. As light from the cosmic microwave background passes through such an immense void, it must climb out of a gravitational well that is becoming shallower due to the accelerating expansion of the universe. The photons lose a tiny bit of energy in the process, shifting them to longer, colder wavelengths. For this to work, the void would need to be unimaginably large, perhaps 500 million light-years across, and incredibly empty. The coincidence here is one of alignment and scale. For us to see a cold spot, such a supervoid would need to be positioned directly along our line of sight to that specific part of the ancient sky. Finding a void of that precise, record-breaking size and having it sit exactly between us and the cold spot would itself be a remarkable and unlikely piece of cosmic geometry. Recent galaxy surveys have indeed found evidence of a large underdense region in that direction, but whether it is vast and empty enough to fully explain the cold spot remains hotly debated. The data is ambiguous, leaving the mystery unresolved, so the cold spot persists, a ghostly chill on the map of creation. It is a coincidence of scale and temperature that challenges our models. Is it a statistical ghost, a phantom that will fade with better data? Is it the shadow of a nothingness so profound it defies our understanding of large-scale structure? Or could it be something far more exotic, a fossil imprint from the violent birth of reality, or even a window into a multiverse we can never directly see? This cold patch in the ancient sky is a silent question mark, a reminder that even our best map of the universe's infancy may contain features whose stories we are only beginning to guess. This chilling mystery of the cold spot, a potential bruise on the infant universe, is mirrored by a pattern of alignment that defies explanation on the opposite end of the cosmic scale. Deep within the hearts of the most luminous objects in the cosmos, another coincidence spins a thread across billions of light-years. Astronomers studying quasars, the blazing cores of distant galaxies powered by supermassive black holes, have stumbled upon a finding that feels impossible. The rotation axes of these black holes, separated by unimaginable voids, appear to be pointing in the same direction. Think of a quasar not just as a beacon, but as a cosmic lighthouse. The intense light and jets of matter it emits are often aligned with the spin axis of the central black hole, like a spotlight sweeping from the top and bottom of a spinning top. By analyzing the polarization of light from thousands of these quasars, scattered across a third of the observable universe, researchers noticed something that should not be. The axes of these distant monsters, these isolated engines, showed a significant degree of alignment with each other over distances spanning billions of light-years. According to our fundamental cosmological principle, the universe should be isotropic and homogeneous on large scales. This means that if you look far enough in any direction, the universe should look roughly the same, with no preferred orientation or structure. the random tumble of galaxies and their central black holes over cosmic history should have left their spins pointing in every which direction, a chaotic scattering with no overarching pattern. This alignment of quasars, therefore, is a direct challenge to that bedrock assumption. It is as if you scattered 1,000,000 tops across a continent, and upon returning centuries later, found a majority of them still spinning and leaning toward the same point on the horizon. The statistical significance of this alignment is too strong to easily dismiss as a fluke. The probability of it happening by random chance is exceedingly low, prompting physicists to search for a mechanism that could orchestrate such a grand, cosmic choreography. One compelling idea points to the influence of primordial magnetic fields, woven into the fabric of space-time during the universe's first moments. These are not the magnetic fields of stars or galaxies, but vast, relic fields stretching across the cosmos. If such fields existed, they could have influenced the direction in which gas collapsed to form the first supermassive black holes, imparting a preferred spin axis that has persisted for over 13 billion years. Another, even more exotic possibility involves cosmic strings, hypothetical defects in spacetime that are thinner than an atom but stretch across the entire universe, possessing immense gravitational influence. A network of these strings could have acted as a scaffold, guiding the angular momentum of collapsing matter on the largest scales. The implications are staggering. It suggests that the universe's largest structures, the great walls and filaments of the cosmic web, might not have formed in a perfectly random, isotropic soup. Instead, there may have been an underlying directionality, a subtle grain to the cosmos imprinted at its birth, that guided the spin of the most violent objects within it. This alignment feels like a profound coincidence because it connects events and objects that, according to standard physics, should have no way of communicating or influencing each other across such vast reaches of space and time. It hints that the local rules we observe, the chaotic and independent evolution of galaxies, might be superimposed on a deeper, more ordered canvas we are only beginning to perceive. Are we seeing the faint signature of the universe's initial conditions, a fingerprint left on the spin of black holes? Or is this alignment a clue to a deeper layer of connectedness in the cosmos, a physics that links the very large to the very first moments in a way we have yet to understand? This grand alignment of quasars hints at a cosmos with a hidden grain, a subtle directionality written into its first moments. But when we try to measure the most fundamental story of all, the rate at which the universe is expanding, that hidden order seems to break down entirely. We are now facing a crisis in cosmology known as the Hubble tension, and it is a coincidence so precise and so stubborn it threatens to rewrite our understanding of reality. The problem is deceptively simple. How fast is the universe expanding right now? The number that answers this question is called the Hubble constant. For decades, astronomers have refined two powerful, independent methods to measure it. The first method looks back to the dawn of time, to the cosmic microwave background. By analyzing the subtle patterns in that ancient afterglow, scientists can calculate what the expansion rate must have been in the infant universe, and then use our standard model of cosmology to predict what the rate should be today. This is like calculating how fast a car is going now based on a photograph taken at the start of its journey and a perfect knowledge of its engine. The second method looks at the universe around us, measuring distances and speeds of nearby stars, galaxies, and especially a special class of exploding stars called Type 1, a supernova. These supernovae are cosmic standard candles, meaning they always explode with roughly the same intrinsic brightness. By observing how bright they appear from Earth, astronomers can calculate their precise distance. By then measuring how much their light has been stretched or redshifted by the expansion of space, they can directly calculate the current expansion rate. This is like putting a radar gun on the car to measure its speed right now. Both methods are exquisitely precise, backed by Nobel Prize-winning science. And they disagree. The measurements from the early universe, the cosmic microwave background, give a Hubble constant of about 67 kilometers per second per megaparsec. The measurements from the local universe, from supernova and other stars, give a value of around 73. The difference is only about 6, but the uncertainty in each measurement is smaller than that gap. This is not a minor discrepancy, it is a direct conflict. Imagine two supremely accurate clocks, one built by studying the first tick of creation, the other built by observing the most reliable rhythms in the modern cosmos. They are supposed to tell the same time, but one consistently runs faster than the other. This is the Hubble tension. The coincidence here is the mismatch itself. It is not a wild, chaotic disagreement, but a clean, persistent offset that has survived over a decade of increasingly precise observations. Every time a team refines their measurements, hoping the gap will close, it remains. This tells us it is likely not a simple error. It could be a hidden systematic mistake, some subtle effect in how we measure distances or interpret the cosmic microwave background that we have not yet caught. But as each potential error is investigated and ruled out, the possibility grows that this tension is real and that it is a signal of new physics. Perhaps our standard model of cosmology, the lambda cold dark matter model, is incomplete. Maybe dark energy, the mysterious force accelerating the expansion, is not constant but changing over time. Could there be an unknown type of neutrino or an interaction between dark matter and dark energy that alters the expansion history? Some even speculate about early dark energy, a burst of repulsive force in the universe's first moments that would have subtly changed the initial conditions read from the cosmic microwave background. The Hubble tension is more than a technical problem for astronomers. It is a cosmic coincidence that keeps scientists awake at night because it represents a direct challenge to the story we tell about the universe from its birth to its present age. Two perfectly valid roads, both paved with impeccable data, are leading us to two different destinations. One road starts at the beginning, the other starts here and now. They should meet seamlessly, but instead, they point to different futures. This tension is a silent alarm bell ringing from the heart of cosmology, a reminder that the universe may still be holding its deepest cards close, and that the numbers we trust to define reality might be telling us a story we have not yet learned how to hear. This fundamental disagreement over the universe's expansion rate points to a flaw in our cosmic ledger, a crack in the accounting of reality itself. But there is another, far older accounting error, one written into the first moments of existence, and its resolution is the single reason you are here to read these words. The universe should be empty. According to our best theories, the Big Bang should have created perfect symmetry, equal amounts of matter and antimatter. For every proton, there should have been an antiproton. For every electron, a positron. Matter and antimatter are opposites in every sense, and when they meet, they annihilate in a flash of pure energy, leaving nothing behind. If the early universe had been perfectly balanced, every particle of matter would have found its antimatter twin. The entire cosmos would have dissolved into a uniform sea of radiation, a boring, featureless glow with no atoms, no stars, no planets, and certainly no people. Yet, here we are, in a universe made almost entirely of matter. This is the matter-antimatter asymmetry problem, and it is one of the most profound mysteries in all of physics. Somehow, in that first searing instant, the balance was broken. For every 1 billion annihilations, one single matter particle was left over, 1 in a billion. That is the entirety of the visible universe, every galaxy, every star, every rock and tree and living creature, built from the leftover crumbs of a near-total annihilation. This tiny, almost negligible excess is the ultimate cosmic coincidence. It is a number so small, yet its consequence is everything. Physicists call the process that could create this imbalance baryogenesis. For it to happen, 3 specific conditions, outlined by the physicist Andrei Sakharov, had to be met in the early universe. First, there needed to be a violation of something called baryon number. Baryons are particles like protons and neutrons, the heavy building blocks of atoms. Normally, the total number of baryons in the universe is conserved. They cannot just appear or vanish. But in the extreme heat of the first second, some process must have broken this rule, allowing a net production of matter over antimatter. Second, the universe had to be out of thermal equilibrium. It could not be a perfectly smooth, uniform soup. There needed to be a disturbance, a departure from perfect balance, for the asymmetry to get a foothold and not be immediately wiped out. The rapid expansion of the universe likely provided this, creating a brief window where processes could run in one direction but not easily reverse. The third, and most elusive condition, is known as CP violation. C stands for charge conjugation, which means swapping a particle for its antiparticle. P stands for parity, which is like looking at the universe in a mirror. For a long time, physicists believed the laws of physics were symmetric under both C and P operations. A reaction involving matter should look the same as its mirror image involving antimatter. But nature, it turns out, has a slight preference. In certain rare subatomic processes, like the decay of particles called kaons and B mesons, scientists have observed CP violation. The mirror image of the reaction happens at a slightly different rate. It is a tiny effect, but it proves the symmetry can be broken. This is the only known ingredient we have that could explain the matter-antimatter asymmetry, but there is a devastating problem. The amount of CP violation we have measured in our particle accelerators is far, far too small. By many orders of magnitude, it is insufficient to produce the 1 in a billion surplus we see in the cosmos. So the mystery deepens. We have found a possible mechanism, but our known version of it is far too weak. This means the CP violation we see in the lab is just a faint shadow of a much more powerful process that must have occurred in the early universe, a process now lost to time. The coincidence, therefore, is not just the existence of the asymmetry, but its specific, precise magnitude. Why 1 extra particle per billion? Why not 1 per million, which would have created a denser, wildly different universe? Why not 1 per trillion, which might have left too little matter for galaxies to ever form? The number had to be within a razor-thin window, too small, and gravity could never have pulled the sparse matter together. Too large, and the universe might have collapsed back on itself far too soon under the weight of all that extra material. Once again, we are faced with a parameter that feels tuned. It is as if the universe, in its first furious second, conducted a perfect, violent subtraction, leaving behind exactly the residue needed to build a cosmos that could one day wonder about its own existence. All the matter you see, from the screen in front of you to the stars above, is the ghostly afterimage of a near-perfect cancellation, a single vote that decided the fate of reality. That single vote for matter over antimatter set the stage for a cosmos of structure, but structure itself depends on something even more fundamental, the very stage upon which the drama unfolds. The universe we perceive is built upon a specific and peculiar scaffolding, 3 dimensions of space and 1 of time. This is not a trivial fact. It is the ultimate setting for every law of physics, every orbit, every chemical bond, and it feels like the most profound coincidence of all. Why 3 and 1? Why not 2 dimensions of space, making our world a flat, infinitely thin sheet? In such a universe, life as we know it would be impossible. Digestive tracts would sever an organism in 2. Complex, interconnected neural networks could not exist without wires crossing. The very concept of knots falls apart. Gravity, as described by physics, would behave bizarrely, with force diminishing so rapidly with distance that stable solar systems could never form. A 2-dimensional cosmos would be a prison of simplicity, incapable of hosting the intricate machinery of life. On the other hand, consider a universe with 4 large spatial dimensions. The mathematics of gravity tells us that in such a world, the force would diminish so quickly that planets could not maintain stable, elliptical orbits around their stars. They would either spiral in or fly off into the void. The delicate balance that allows Earth to circle the Sun for billions of years, within a narrow temperature band conducive to life, relies critically on the inverse square law of gravity, a law that exists only in 3 spatial dimensions. In 4 dimensions, it would be an inverse cube law, and orbital motion would become chaotic and transient. Even the structure of atoms becomes unstable with extra dimensions. Electrons would not form stable shells around nuclei, and chemistry, with its vast periodic table of elements and complex molecules, would simply not work. The number 3 for space is a Goldilocks setting, not too few, not too many, but just right for the emergence of stable, complex systems. Time presents its own unique puzzle. We experience time as a single, relentless dimension flowing in one direction, from past to future, governed by the increase of entropy, the universe's tendency toward disorder. But why only 1? Some physical theories, like string theory, mathematically allow for many more dimensions, perhaps 10 or 11 in total. The idea is that the extra dimensions beyond our familiar 3 of space and 1 of time are curled up, or compactified, on a scale so incredibly tiny, a billion times smaller than an atomic nucleus, that they are completely invisible to us. Our entire universe, with all its galaxies and stars, might be a 3-dimensional membrane floating within a higher dimensional space, with the other dimensions tightly wound up at every point. This is not science fiction, but a serious attempt by physicists to unify gravity with quantum mechanics. Yet, this very solution highlights the coincidence. Out of all the possible ways these extra dimensions could have curled up, the universe settled into a configuration where exactly 3 expanded to an astronomical size, and 1 became the arrow of time we experience. The specific compactification that led to our reality appears breathtakingly special. It produced the inverse square law of gravity. It allowed for stable orbits and atoms. It permitted the formation of planets, stars, and galaxies. It enabled the one-way flow of causality and memory that is essential for consciousness itself. We do not just live in a universe with 3 + 1 dimensions. We live in a universe where that specific geometry makes our existence possible. the stage itself seems tailor-made for the play. This foundational setting feels less like a random outcome of cosmic inflation and more like a prerequisite, a non-negotiable condition written into the foundation of reality, without which none of the other coincidences could ever have mattered. The stage of our 3+1-dimensional universe seems perfectly set, but that very perfection leads us to a dizzying precipice of doubt. What if the stage, the play, and even our own memories are not what they seem? This is the Boltzmann brain paradox, a thought experiment so unsettling it questions the fundamental reliability of our own existence. It begins with a simple law of physics, the second law of thermodynamics, which states that entropy, or disorder, always increases in a closed system. A cold drink warms up in a hot room, a neat desk becomes cluttered. The universe itself is marching from a state of low entropy at the Big Bang toward a future of maximum disorder, a featureless, cold equilibrium known as heat death. But here is the twist. In a universe that lasts for an eternity, even the most wildly improbable events become not just possible, but inevitable, given enough time. In the vast, cold emptiness of the far future, trillions upon trillions of years from now, random quantum fluctuations in the void could, by pure chance, spontaneously assemble a fully formed, self-aware brain, complete with all the memories and sensory experiences of a lived life. This phantom consciousness is called a Boltzmann brain, named for the physicist Ludwig Boltzmann, who first grappled with these ideas. The paradox emerges from a brutal statistical calculation. In an eternally expanding universe heading toward heat death, which event is more probable? The random, spontaneous fluctuation of a single, self-aware brain out of the quantum foam, or the immensely ordered, low-entropy evolution of an entire 13.8 billion-year-old cosmos, with all its galaxies, stars, planets, and the intricate history that led to you sitting here, thinking these thoughts. The numbers are terrifying. A single, disembodied brain with a brief flash of false consciousness is astronomically more likely than the existence of our vast, coherent, and ancient universe. It requires far less of a statistical miracle. So, the paradox forces a horrifying question. Are we the legitimate products of a long, ordered cosmic history, or are we merely Boltzmann brains, momentary flickers of awareness that just think we have a past and a universe around us? This is not science fiction. It is a legitimate philosophical and cosmological problem that arises directly from our current understanding of thermodynamics and an eternal universe. The fact that we perceive a consistent, law-governed reality that stretches back billions of years, rather than a fleeting, nonsensical hallucination, is itself a staggering coincidence that demands an explanation. Why does our experience feel so real, so continuous, and so deeply interconnected? One escape from this paradox is to conclude that the universe is not eternal in the way that leads to heat death. Perhaps the cosmos will end in a big crunch or a cyclical rebirth, preventing the infinite time needed for such fluctuations to become inevitable. Or perhaps the vacuum of space is not entirely stable, and our universe will eventually decay into a different state, again cutting the timeline short. Another possibility is that our current cosmological model is missing a crucial piece that makes the evolution of our ordered universe more probable than the freak accident of a Boltzmann brain. Some interpretations of quantum mechanics or theories of the multiverse might provide a statistical bias toward large, coherent realities like our own. But the chilling core of the paradox remains. It uses the very laws of physics to undermine our trust in those laws and in our own memories. it suggests that the greatest cosmic coincidence of all might be that our seemingly solid reality is, in fact, real. We are left confronting the possibility that the most rational conclusion from our best physics is also the most absurd, that we are far more likely to be phantoms than people. This paradox does not offer answers, only a profound and humbling unease, a reminder that at the edge of understanding, the universe can question the very mind that seeks to understand it. That existential doubt, that we might be phantoms in a cosmic void, leads to one final, modern interpretation of the cosmic coincidence problem. It is an idea that has leapt from science fiction into serious philosophical debate. The simulation hypothesis. Its logic is disarmingly simple, built on a statistical argument about the future of intelligence. Imagine a technologically advanced civilization, perhaps thousands or millions of years ahead of us. Its computing power would be godlike. One of the most profound uses of such power might be to run detailed, immersive simulations of reality, perhaps to study history, test theories, or even for entertainment. They could create countless simulated worlds, each populated with conscious, simulated beings who believe their reality is genuine. Now, consider the numbers. If even one such civilization exists and runs many simulations, the total number of simulated minds would quickly dwarf the number of original, biological minds in the base reality. Therefore, if you are a conscious being, the statistical probability is overwhelming that you are a simulation, not a base reality entity. You are far more likely to be one of the countless digital inhabitants than one of the rare, original creators. This is not proof, but a probabilistic argument, and it reframes every single cosmic coincidence we have explored: the fine-tuning of the constants, the mathematical beauty of the laws, the eerie numerical echoes, the inexplicable anomalies. In a simulated reality, these are not mysteries of fundamental physics. They are artifacts of the code. They are the programmed parameters, the fixed rules of the simulation, perhaps even the glitches in the matrix. The universe feels mathematically elegant because it is mathematics, rendered in exquisite detail. The cosmological constant is a strange number not because of quantum vacuum energy, but because the programmer chose that value, or it emerged from the underlying algorithms. The matter-antimatter asymmetry is a set variable, not a relic of a primordial battle. Even the Boltzmann brain paradox takes on a new light. In a simulation, your coherent memories and consistent reality are not a statistical miracle. They are simply the data stream being fed to your consciousness. The simulation hypothesis offers a chillingly clean answer to why the universe seems so suspiciously well arranged. It is arranged, it is designed, but this idea, while compelling, pushes the coincidence one step further back. Who created the simulators? Their reality would also need laws of physics capable of supporting complex life and computation. Their universe would also likely exhibit fine-tuning and mathematical order. So we are left with an infinite regress, a cosmic hall of mirrors. Are we in a simulation within a simulation within a simulation? The hypothesis does not solve the ultimate mystery of existence, it merely relocates it. Yet it stands as the final, ultimate expression of the cosmic coincidence problem. It suggests that the deepest layer of reality might not be a realm of unknowable physical laws, but a realm of information. The universe is not just described by mathematics, it may literally be a mathematical structure, a computation, and we, with our capacity to notice the patterns, the strange alignments, and the perfect numbers, might be the first hints that the program is becoming self-aware, starting to question the nature of the reality it finds itself in. It is the final, haunting thought. Perhaps we are not discovering the secrets of the cosmos, but slowly, painfully, reverse engineering the source code. 30 distinct mysteries, each a whisper of something strange. Taken individually, any one could be a fluke, a measurement error, or a gap in our knowledge. But together, they form a chorus singing a single, unsettling question. Is the universe trying to tell us something? When we step back and look at these 30 cosmic coincidences as a whole, patterns begin to emerge from the chaos. They seem to fall into 3 broad, overlapping categories. The first is fine-tuning. This is the eerie sense that the dials of reality are set with impossible precision. The strength of gravity, the mass of the electron, the energy of empty space, the initial density of the cosmos, all calibrated to values that allow for stars, planets, and life. If any one were different by a hair's breadth, the universe would be a barren void. The second category is statistical anomalies. These are events or alignments that should not happen according to our best models. The axis of evil in the cosmic microwave background, the perfect alignment of the sun and moon, the strange flyby anomalies of our spacecraft, the lithium deficit in the early universe. They are outliers in the data, stubborn facts that refuse to fit neatly into our equations. The third theme is anthropic selection. This is the logical, yet deeply unsatisfying, idea that we observe this particular universe simply because we are here to observe it. In a vast multiverse where every possible set of physical laws exists, we naturally find ourselves in one of the rare, habitable bubbles. It answers the question of why the constants are life-permitting, but it feels like explaining the existence of your house by saying all the other possible houses burned down. So, what are we to make of this collective puzzle? Are these 30 coincidences truly independent clues, or are we, as pattern-seeking creatures, connecting dots that are not truly linked? Our brains are wired to find meaning, to see faces in clouds and conspiracies in randomness. Could this entire exercise be a magnificent example of cosmic pareidolia, where we impose a narrative of design onto a universe that is, at its heart, random and indifferent? It is a possibility we must take seriously. Yet, the sheer number and precision of these alignments make that explanation feel increasingly strained. When the same razor's edge appears in the nuclear resonance that creates carbon, in the flat geometry of space, and in the timing of our own cosmic dawn, it begins to feel less like seeing shapes in the clouds and more like recognizing the consistent brushstrokes of a single artist. This leads to the second, more thrilling possibility. Perhaps these are not coincidences at all, but hints, scattered clues pointing toward a deeper layer of reality we have not yet uncovered. They could be the emergent shadows of a grand unifying theory, a theory of everything that would naturally explain why the constants have the values they do, why the universe is flat, and why matter won out over antimatter. In this view, the numbers are not freely adjustable dials, but the inevitable outcomes of a single, elegant mathematical principle. Alternatively, the clues might point outward, beyond our own universe. The multiverse hypothesis, for all its philosophical strangeness, provides a direct, if untestable, framework for the anthropic principle. In an infinite ensemble of universes, every possible combination of constants is realized somewhere. We simply reside in one that allows for our existence. The fine-tuning is not a design, but a selection effect. The anomalies, however, like the quasar alignments or the cold spot, might then be scars or echoes from collisions with other universes in the greater multiversal foam. What is truly important is not which answer we prefer, but the act of asking the question itself. Confronting these 30 problems is not a sign that science is failing. It is the exact opposite. This is how science progresses. Every great leap in understanding began with an anomaly, a coincidence that refused to go away. The unexplained motion of Mercury's orbit was a clue to general relativity. The strange stability of matter hinted at the atomic nucleus. The cosmic coincidence problem, in all its sprawling complexity, is the frontier. It is the universe presenting us with its deepest riddles. Whether the answer is a deeper law, a vaster cosmos, or a profound lesson about our own perception, the pursuit transforms us. It forces us to question our most basic assumptions, to build better telescopes and more powerful colliders, and to think with more humility and more courage than ever before. The silence is not an ending, but an invitation to listen more closely. From the fundamental constants of physics to the chemistry in our veins, the journey through these 30 cosmic puzzles paints a portrait of a universe that is profoundly, persistently strange. We have moved from the vast, cold expanse of the cosmic microwave background to the perfect alignment of our own moon and sun. We have seen how the spin of distant black holes might whisper of a universal grain, and how the very water in our glass defies expectation to cradle life. Each mystery, whether a number too precise, a pattern too aligned, or a silence too deep, stands as a sentinel at the edge of our knowledge. They are not failures of science, but its fuel. These coincidences define the current frontier, the unanswered questions that keep physicists and philosophers awake at night, staring at equations and star charts, searching for the next thread to pull. So, where does this leave us after wandering through this gallery of cosmic curiosities? The evidence, or perhaps the lack of it, forces a choice upon you, the observer. When you look at this collective picture, what do you see? Is it a universe of magnificent accidents, a cosmic lottery where we hold the one in a Googleplex winning ticket? Is it the subtle fingerprint of a deeper order, a design or a simulation where the parameters were set with intention? Or are these 30 clues pointing toward a reality far stranger and more wonderful than we have yet dared to imagine? A multiverse, a cyclic cosmos, or a physics we have not yet invented? The answer you lean toward says as much about you as it does about the universe. This conversation does not end here. The search for answers is a human endeavor, and your perspective is part of it. If this exploration of the cosmos's greatest mysteries resonated with you, consider liking this video and subscribing to join us for more journeys to the edge of understanding. And most importantly, we want to hear from you. Look back through these 30 cosmic coincidences. Which one chills you the most? Which one feels like the strongest hint of something deeper? Share your favorite in the comments below. Let's continue this conversation among the stars.